Hello everyone. Welcome to SHR Trinity. In our previous video, we explored zero-shot prompting. Today, we advance to the next critical technique, chain-of-thought prompting. In this video, we will cover the foundational interview questions on chain-of-thought prompting, explaining how providing just a single example can drastically improve a model's accuracy and format adherence. Let's get started. Before we begin, if you're looking for practical, industry-oriented training in artificial intelligence and generative AI, SHR Trinity offers a comprehensive 30-hour training program. For complete course details, check the description below. Now let's begin today's interview session. We will now begin with the interview questions for chain-of-thought prompting, Part 1, Basic Fundamentals. Moving on to our next question, what is chain-of-thought, CoT, prompting and how does it differ from standard prompting?
Hello everyone. Today we're exploring chain of thought, or CoT, prompting and why it fundamentally differs from standard prompting. When you use standard prompting, you're asking the model to jump directly to a final answer in a single feed-forward pass. For simple tasks, that works fine. But for complex logic, forcing an immediate output starves the model of computational depth. CoT fixes this by explicitly guiding the model to generate intermediate reasoning steps before providing the final output. Think of it like showing your work on a math exam rather than just guessing the final number. Mathematically, each intermediate token generated gets appended back into the prompt context window. This gives the self-attention mechanism additional compute budget and concrete logical anchor points to reference for downstream calculations. Let's look at our example to see this in practice. Imagine asking a word problem. Roger starts with 5 tennis balls and buys 2 cans of 3 balls each. How many does he have? Standard prompting immediately tries to predict 11, which often leads to errors in harder problems. In contrast, a CoT prompt leads the model through step-by-step logic. First, state that Roger starts with 5. Second, compute that 2 cans of 3 equals 6. Third, add 5 and 6 to get 11, and finally, present 11 as the answer. By walking through each logical step, we turn hidden, internal neural processing into explicit, reliable, step-by-step reasoning.
Moving on to our next question, how does chain-of-thought prompting activate intermediate reasoning tokens in LLMs?
Let's dive into the mechanics of how chain-of-thought prompting actually activates intermediate reasoning tokens inside a large language model. You see, transformers generate text autoregressively. This means that every single token the model outputs is immediately fed back into its context window as input for the very next token. When we use CoT, we force the model to write out its intermediate logic into this generation buffer. Rather than expecting the model's self-attention layers to compute a multi-step logical jump in a single forward pass, which is limited by the model's fixed layer depth, those intermediate tokens function as a form of external working memory via dynamic inference time allocation. The self-attention mechanism can now explicitly attend back to these previously generated token anchors to perform the next logical step with much higher accuracy. To see how crucial this is, consider our example of multi-digit multiplication. If you ask a model to multiply 2 large numbers instantly, standard prompting fails because it tries to calculate the answer in one single jump. But with CoT, the model generates intermediate lines of arithmetic. In step 1, it computes partial products, in step 2, it aligns columns, and in step 3, it adds carrying values. The self-attention heads continuously look back at these written intermediate calculations, ensuring that each subsequent step builds on solid, verifiable data rather than hitting a context blind spot.
Moving on to our next question, in what specific problem domains does chain-of-thought prompting yield the highest accuracy gains?
Welcome back. Today we are looking at where chain-of-thought prompting delivers the highest return on investment. While CoT is powerful, it isn't necessary for every task. Its true superpowers emerge in domains requiring multi-step logical synthesis, specifically arithmetic reasoning, symbolic logic manipulation, multi-step common sense reasoning, and code debugging. Empirical research on benchmarks like GSM-8K for grade school math and SVAMP shows remarkable results. When switching from standard zero-shot prompts to few-shot CoT on large models over 100 billion parameters, accuracy scores frequently jump from a dismal 15 to 30% all the way up to 70 to 90%. Why? Because these domains require sequential state tracking. On the flip side, simple retrieval tasks, like asking what is the capital of France, show zero accuracy improvement with CoT, merely burning extra tokens needlessly. Let me ground this with our real-world examples. Think about evaluating multi-nested conditional logic in code or parsing complex legal contract clauses. If you present a legal clause with multiple conditional qualifiers, such as if party A defaults and notice is given within 30 days, unless force majeure applies, a standard prompt struggles to weigh every condition simultaneously. CoT forces the model to check condition 1, evaluate condition 2, assess the force majeure exception, and then reach a bulletproof legal conclusion step by step.
Moving on to our next question, what is the fundamental difference between manual CoT and few-shot CoT prompting?
Let me clarify a crucial distinction in prompt engineering: manual chain of thought versus few-shot chain of thought prompting. In practice, these terms are often combined, but understanding their distinct roles is essential. Manual CoT refers to the human effort of explicitly crafting step-by-step reasoning pathways, while few-shot CoT refers to providing a small set, typically 2 to 5, of these crafted exemplar pairs directly within the prompt context before asking the target question. When you provide these manual exemplars, the model performs in-context learning. It doesn't just learn the output format, it adopts the precise logical decomposition strategy demonstrated in the exemplars. However, this creates a major point of failure. If a human engineer writes an exemplar containing a subtle mathematical mistake or flawed logic, the LLM will faithfully replicate that exact flaw in its own downstream reasoning. To illustrate this, consider our physics problem example. Suppose we want an LLM to solve complex kinematics queries. In a manual few-shot CoT setup, we write out 3 distinct exemplar questions in the system prompt. For each exemplar, we show the question, explicitly state Step 1, identify given variables, Step 2, select the kinematic formula, and Step 3, solve for the unknown. When the user presents a brand new, unseen physics problem, the model follows that exact structured, step-by-step analytical pathway it observed in the exemplars, ensuring a reliable and structured solution.
Moving on to our next question, how does the choice of reasoning step phrasing impact the model's intermediate logic?
Today we're discussing how the subtle phrasing of reasoning steps directly controls an LLM's intermediate logic. Because language models are pattern-matching engines trained on vast textual datasets, the structural markers you use in your prompts act as powerful navigational anchors for the model's attention mechanisms. If you use loose, conversational phrasing like "well, let's see what happens next," you risk introducing noisy tokens that distract the self-attention heads from the actual computational task. Conversely, using explicit, structured markers, such as Step 1, therefore, or XML tags like reasoning, signals clear syntactic boundaries. These markers guide the model to transition smoothly from variable identification, to intermediate calculation, and finally to logical synthesis. Let me walk through our structured template example to see why this is so effective. Imagine structuring a prompt with explicit headers. Step 1, identify given variables. Step 2, formulate the equation. Step 3, compute subtotals. And Step 4, state final conclusion. When the model executes Step 1, its attention focuses solely on extracting raw facts. As it hits the trigger phrase Step 2, it shifts focus entirely to math logic. By enforcing this clear structural cadence, you eliminate ambiguity and drastically lower the risk of logic slipping off track during intermediate inference.
Moving on to our next question. Why does standard prompting fail on multi-step math and logic puzzles while CoT succeeds?
Why do standard prompts fail miserably on complex math and logic puzzles, while chain of thought prompting succeeds? To understand this, we have to look at transformer architecture. In standard prompting, the model is required to compute the final output token immediately following the prompt, using only a single forward pass through its neural layers. A model with 80 layers only has 80 transformations to figure out the final answer. Complex multi-step problems require dynamic computational depth. Think of standard prompting like forcing a human to solve a 5-step calculus problem in their head in under 1 second without scratch paper. It's nearly impossible. CoT solves this by distributing the computation across sequential token generation steps. Every intermediate token written out effectively gives the model another forward pass, expanding its compute budget dynamically. Let me examine our chess puzzle example to visualize this difference. If you show a standard prompt a complex chess position and ask for the best move, it tries to predict the final grandmaster move instantly in one single pass, often choosing an obvious but flawed tactical blunder. In contrast, a CoT prompt forces the model to evaluate step by step. If white plays bishop to g5, black can respond with knight to f6. If black moves knight to f6, white has a forced checkmate. By explicitly simulating the opponent's intermediate countermoves first, the model accumulates the necessary contextual logic to arrive at the correct winning move.
Moving on to our next question, what is reasoning degradation in CoT prompting and how do you prevent it?
Let's address a major edge case in advanced prompt engineering, reasoning degradation. Because language models generate text autoregressively, every token produced conditions every token that follows. If the model introduces a slight hallucination or mathematical miscalculation early in a long chain of thought trace, that error becomes part of the authoritative context. This creates a snowball effect. Early errors compound downstream, causing the model to drift off topic, enter repetitive logic loops, or reach completely absurd conclusions despite looking superficially logical. To prevent reasoning degradation, engineers must implement structural guardrails. This includes enforcing strict step limits, requiring intermediate validation tags, or using self-consistency, a technique where you generate multiple CoT paths in parallel and take a majority vote on the final answer. Look at our financial forecasting example to see how dangerous degradation can be. Imagine a 10-step financial projection model. In step 2, the LLM hallucinates an incorrect corporate tax rate of 15% instead of 21%. Because subsequent steps depend on step 2, steps 3 through 10 will flawlessly apply correct algebra to an invalid premise, resulting in millions of dollars in projected variance on the final line item. By applying strict intermediate constraints or validation checks at each step, we catch that tax error before it ruins the entire downstream analysis.
Moving on to our next question, how does context window size impact long multi-step chain of thought reasoning traces?
Now let's analyze the systemic trade-offs between chain of thought reasoning traces and context window limitations. While modern LLMs offer expansive context windows reaching up to 1 million tokens, generating thousands of intermediate reasoning tokens isn't free. When a model generates an extended CoT trace, every single intermediate token consumes context memory, increases quadratic self-attention computation, and adds directly to latency. You'll notice spikes in both time to first token and total response completion time. Furthermore, if a reasoning trace becomes excessively bloated, it runs the risk of degrading focus on original system prompts or early user constraints due to context dilution. To optimize performance, we often impose explicit concise constraints, instructing the model to keep reasoning under 150 words or use maximum 3 logical steps. Consider our example of an enterprise multi-agent auditing pipeline. Imagine processing 10,000 legal contracts where each document agent generates 5,000 internal reasoning tokens before delivering a simple summary. Multiplying those tokens across thousands of calls creates massive network latency and ballooning cloud infrastructure bills. By tuning the prompt to keep CoT traces concise and tightly focused on necessary logical steps, you maintain high reasoning accuracy while preserving fast throughput and low latency.
Moving on to our next question, can chain of thought prompting be combined with structured output constraints like JSON?
A very common question in production AI architecture is, can we combine chain of thought prompting with structured output formats like JSON? The answer is an emphatic yes, but you must structure the output schema very carefully. A frequent mistake engineers make is forcing an LLM to return strict JSON where the very first character must be the open curly brace followed immediately by the final answer key. When you do this, you effectively force the model to compute the final answer in its very first generation step, completely bypassing its ability to use intermediate reasoning tokens. Accuracy plummets as a result. To solve this, you must structure your JSON schema or XML delimiters so that a designated reasoning field appears before the final answer payload key. Let's walk step by step through our example JSON schema: reasoning_steps, final_answer, confidence_score, 0.95. When the LLM generates this payload, it hits reasoning_steps first. It writes out its detailed, step-by-step logical deduction directly into that string value. By the time it finishes that field and reaches final_answer, those generated reasoning tokens are now part of its active context window. The model can easily pull the correct conclusion from its own written reasoning, giving you both top-tier reasoning performance and structured, machine-readable JSON.
Moving on to our next question: what are the cost, latency, and token consumption trade-offs of using chain-of-thought prompting?
Finally, let me address the financial and operational reality of chain-of-thought prompting: cost, latency, and token consumption trade-offs. While CoT dramatically boosts accuracy on complex tasks, it comes at a measurable computational cost. On average, CoT increases completion token output by 3x to 10x per request. Because API providers charge significantly higher rates for output tokens than input tokens, and because generation latency scales linearly with output length, generating 300 intermediate reasoning tokens just to deliver a 10-token final answer can increase your cost per API call by 30 times. Applying CoT indiscriminately to every incoming query, including simple classifications or fact lookups, is a major architectural mistake. The solution is to build a dynamic routing architecture that sends simple queries through standard zero-shot prompts and routes complex analytical queries through CoT pipelines. Let me take a look at our enterprise example. Imagine an automated email classification pipeline processing 100,000 support tickets a day. Under standard zero-shot prompting, the system costs $100 per day. If an engineer blindly turns on full chain-of-thought reasoning across all tickets, the operational cost jumps to $800 per day with zero accuracy gain on basic routine categorizations. By implementing routing rules, you reserve expensive CoT reasoning tokens only for complex edge cases, optimizing both budget and latency.
Excellent. You've completed Chain-of-Thought Prompting, Part 1, Basic Fundamentals. In the next video, we'll dive deeper into using one-shot prompting to enforce strict JSON and XML outputs for API integrations. If you found this video helpful, please like, share, subscribe to SHR Trinity, and press the notification bell so you never miss our upcoming AI interview preparation videos. Thank you for watching. See you in the next video.